Okay, so well, welcome everybody to this talk. Thank you for inviting me to present some of my ideas to you. And so today I'm going to talk about using quantum probability to understand contextual reasoning. So what I mean by contextual reasoning is that the way we reason about events depends upon the context of the questions that we're asking. So, like the probabilities that we assign these events can be affected by the context of the questions that we're asking about them. And that poses problems for traditional, probability theories like Bayesian probability theories. And quantum theory seems to be ideally suited for representing these kinds of contextual effects. So let me start with some examples of contextual reasoning to make this a little more concrete. So let's take a look at what we call the conjunction fallacy. This is a well-studied phenomena in cognitive psychology. It was originally discovered by Tversky or Kahneman and Tversky in 1983. But before I get to the uh, some of the experiments by Kahneman, Tversky and Kahneman, let me start with an interesting example. Let's start with an AI example, large language model example. So. Um, yeah, Jeffrey Hinton, who just won the Nobel Prize recently, gave an interview on 60 Minutes, and he was suggesting that pretty soon AGI could make important contributions to medical diagnosis. I think my wife told me that Musk said that pretty soon you don't need to go to medical school, we'll just use artificial intelligence. Okay, so that's a prelude to what I'm going to show you here. Well, anyway, I asked ChatGPT. Now, this question was asked a couple years ago, and ChatGPT is changing a lot, so I haven't checked this recently. Some of my colleagues have been checking some of these things on large language models recently, and they still find these issues that I'm going to present here. But anyway, here's a question I presented to ChatGPT. Um, I have a question about a woman named Mary, and she's 55 years old, and she had a pulmonary embolism documented angiographically 10 days after a cholecystectomy. I have trouble pronouncing some of these words. Okay, so that's a medical kind of condition. And so I asked ChatGPT, choose one of the following three conditions as the most likely that Mary will experience now. Condition one, hemiparesis is one of the experiences. Condition two, dyspnea and hemiparesis are both some of the experiences. And condition three, she experiences hemiparesis but not dyspnea. So that's what I asked ChatGPT. Now, if ChatGPT's reasoning um, in a contextually free way uh, and placing all these events, like dyspnea and hemiparesis in a common probability space, which is commonly done in Bayesian models, then of course we have to have the conjunction assign the probability less than one of the marginals because we have this joint probability space and the conjunction in the upper left-hand cell, DNH has to be less than the margin on the far right, P of H. So that's what we expect if these events are all coming from a common probability space. Uh-oh, I'm missing a slide. I'm sorry. Somehow I lost the slide. Oh, here it is. I got it out of order. Okay, well, what was the answer by ChatGPT? Sorry, I messed around with my slides and got them out of order. Okay, here's what ChatGPT said. The most likely condition Mary will experience is condition two. Dyspnea and hemiparesis are both some of the experiences. And then ChatGPT went into a convincing explanation, medical explanation, why you might expect dyspnea and hemiparesis to both be some of the experiences. So, that's directly contrary to this uh, common sample space for all these events. It seems like um, you need to separate these sample spaces. So, yeah, let me go further here. So, Yeah, sorry, I got the slides out of order. I don't know how I did that. But yeah, so that's ChatGPT. But that question was based upon earlier work by Tversky and Kahneman. Uh, and so this question was one of the examples that they've studied. They studied many, many different examples. And so this is just one because it's kind of an interesting medical example. And so they actually did one of the studies with real medical interns. So they asked a similar question to medical interns. And so they asked these medical internists, they told them a 55-year-old woman had pulmonary embolism documented angiographically 10 days after a cholecystectomy. And they were asked to judge the probability that each of the conditions below would be experienced by the patient. So, like one of the conditions they had to judge, well, what's the likelihood that they have dyspnea and hemiparesis? What's the likelihood that they have calf pain? What's the likelihood they have pleuritic chest pain? So they were asked to judge the likelihood of all these events. But notice that they were asked to judge the likelihood of dyspnea and hemiparesis, as well as asked to judge the likelihood of hemiparesis by itself. And what they found in their experiment was that the conjunction dyspnea and hemiparesis was given a higher probability, 0.77, than hemiparesis by itself. So apparently, what's happening is that we need to have separate probability space. So when you ask the question about dyspnea and hemiparesis, you got one context, and you have, in a way, one probability distribution where the joint probability gives you 0.77. But then when you ask about his hemiparesis by itself, a separate context, the probability is only 0.45. And so we're getting different probability distributions. We're forced to assume we got different probability distributions depending upon whether we ask the joint event about dyspnea and hemiparesis versus if we ask the single event. So that's an example where the context of the question seems to be changing how we're reasoning about these events. So how we're reasoning about hemiparesis, has been changed, whether it's evaluated in the context of dyspnea. So this conjunction fallacy is pretty robust. It occurs, F and B is from feminist bank tellers. It occurs when you use bets instead of probability judgments. It occurs when you use frequency judgments, and it occurs for all different kinds of scenarios. So it's been studied for about, 40 years now. And so it's one of the, most interesting findings that run against Bayesian probability that has been found in cognitive psychology. So that's the kind of thing that we want to be able to explain with another kind of probability theory. So let's take another example. Here's an example of when people are a categorization decision-making example, I'm going to call it. Okay, and this is an experiment. So people are shown faces, and sometimes they're shown wide faces, and sometimes they're shown narrow faces. And the wide faces tended to be categorized as good guys that you should act friendly to, and the narrow faces were categorized as bad guys that you should attack and be aggressive with. So, but the assignment of the face, like wide or narrow, to good or bad was probabilistic. And the assignment of being rewarded for attacking or withdrawing, depending on good or bad, that was also probabilistic. So it was a probabilistic kind of reasoning task. But we had two conditions in this experiment. In one condition, on some trials, subjects were first asked to categorize the face as good or bad, and then decide whether they wanted to attack or withdraw, and then they were given feedback. So on another kind of trial, we call it decision alone trial, they just decided whether they wanted to attack or withdraw without making any categorization. So we got one context where we're looking at the decision when they first categorized, and we have another context where we look at the decision when they didn't categorize. Now, in the decision alone, presumably, the category should be implicitly coming up in their mind because the category is still important, but we just didn't ask about it. So, supposedly they're implicitly thinking about it, but we didn't ask them to make any judgment about it. So that's the two contexts. Now, if these events, judging good guy or bad guy and attack and withdrawal, if they're all coming from a common probability space, then what we should expect is that the probability that you attack, this first line in this table, should be the sum of the probability that you say it's not a bad guy and you attack, plus the probability that you say it is a bad guy and you attack. So, in other words, the probability that you say it's a good guy and you attack, plus the probability that you say it's a bad guy and you attack. That's the law of total probability in Bayesian models. So if all these events are in a common probability space, then we expect the law of total probability to hold. And so we should find probability of attack is equal to the sum of those two things. But here's the results that we get. This is one of the experiments, and we've replicated this several times. But this is just one of the conditions. So what we see is in this condition, this was a condition where it was a bad guy face, a narrow face. It was a narrow face. So the probability they said it was good was only 0.17. And the probability they would attack, given they said it was good, was 0.41. And the probability they said it was bad was 0.82. And the probability they would attack, given they said it was bad, was 0.63. So the total probability, if we multiply the probability good 0.17 times the probability attack given good 0.41, plus the probability bad 0.82 times the probability attack given bad 0.63, that total probability adds up to 0.59. So in the case where we observe the category and the decision, the total probability to attack turns out to be 0.59. But if in the second condition where we just ask them, do you want to attack or not? Now the category should still be important, but we don't ask them about it. Now the probability of attack turns out to be 0.69, 10% higher than the total probability. And if you look at this table, the probability of attack, when we don't ask them the category 0.9, turns out to be higher than the probability they attack when they just categorized it as a bad guy, 0.63. So again, we're getting some kind of a violation of the common probability space, and to contextualize these probabilities. So we have one probability distribution when we don't ask about the category first and look at the decision to attack. And we have another probability distribution when we first categorize and then decide to attack. And so, whether we ask the question alone versus ask the question in the context of categorization, we get different distributions. So, so this is another example where our reasoning seems to be contextual. It depends on the context of the questions. How we're thinking about attacking depends on whether you first categorize or not. Let's take a look at a third example, question order effects. Okay, this is an example of using a prisoner's dilemma game. I'm assuming people are quite familiar with the prisoner's dilemma game. Let's see here. Are we still okay, everybody?
Yes.
Okay.
Yes, it's going great. Thank you.
Okay, thanks. Yeah. Okay, so here's the prisoner's dilemma game. We got two players like Bill and Ann, and they can either defect or they cooperate. And basically, the payoffs are set up so that no matter what Ann does, Bill's better off defecting. And no matter what Bill does, Ann's better off defecting. So the dominant strategy economics would be, in the economic game theories, would be to defect. But people often cooperate. So that's one issue. But a more interesting issue for us right now is that this tendency to cooperate in the prisoner's dilemma game depends a lot on the order that you ask the questions. They'll tend to cooperate a lot when you ask them to make the action first, like just go ahead and decide your action. But they'll tend to defect more if you ask them to predict their opponent's move first. So we get a big order effect here. So if they predict and then decide, then you get a lot more defection. But if you decide first and then you predict, you get less defection. Now, of course, if these events are all coming from a common probability space, there shouldn't be any order effects because, you know, uh, classic probability, the conjunction is commutative. So the probability that you cooperate and the other person cooperates should be the same as the probability that the other person cooperates and you cooperate. It shouldn't matter which order we ask these questions if they're all coming from a common probability space. But in fact, what happens is it makes a big difference. So the context, in this case, the context is the order that the questions are asked, can greatly affect the results. So we see that when they act first in this left-hand table, the total probability that they cooperate is 0.65, pretty high. The majority of actions is to cooperate when they act first. But when they predict their opponent's move first, that's the right-hand table, the probability they cooperate drops down to 0.42. So the idea of predicting first, decreases their rate of cooperation. So what we see here again is these context effects where the order of the questions changes the context and changes how we reason and think about these events. Yes, so we need two different contexts to represent these tables. One context when one order and a separate context for the second order. So let's take one last example. Oh, I don't know if I maybe got too many examples here. Okay, we'll go through a couple more. We have a lot of examples, so I could spend a whole day on examples, but I want to get to the quantum theory. But we'll go through a couple more examples. So this is an example of what we call a test of contextuality. If you study quantum physics or know something about entanglement and Bell inequality tests, this is like a psychological version of a Bell inequality test. So this experiment is done by my colleague Peter Bruza, paper published in Cognitive Psychology. So he showed people faces like you see on the left here, and he would ask them pairs of questions. So the context is a pair of questions. So for example, in one context, he might ask, is this person intelligent and trustworthy? So is this attribute intelligent true? At the same time, trustworthy is true. So that might be one context. Now, second context, you might ask, is this person intelligent and dominant? That's the second. Then the third context is this person trustworthy and dominant? So those are the three different contexts. They're produced by pairs of questions. And now, if it's all a joint probability space, this will be in this case, a three-way joint probability space. So, if we have a common probability space, then all the probabilities we obtain from these pairwise questions come from a common three-way table by marginalization. So, if we look at the intelligent, trustworthy margins, we just marginalize across the dominance part of the table. And so that would be a three-way joint probability. That's the way the Bayesian models work. They would put all this into a common probability space, and the individual two-way tables would be produced by marginalization. Now, according to this three-way joint distribution, no matter what the joint distributions are, no matter what the dependency is, they need to satisfy this kind of inequality down at the bottom here. This equality at the with this expectation showing is called the Leggett-Garg inequality. It was invented by Tony Leggett-Garg. Tony Leggett just recently died a couple weeks ago. He's a famous quantum physicist. But anyway, according to the Leggett-Garg inequality, the intuitive idea is that this expectation at the bottom is measuring correlations. So it's saying that the correlation between for binary events, the correlation between I and T plus the correlation between T and D minus the correlation between I and D has to be less than or equal to 1. All joint distributions, no matter what they are, have to satisfy that inequality. That's called the Leggett-Garg inequality. Now, the data are shown at the top here. And so if you plug in this data into those expectations, what you get is this inequality at the bottom I'm showing here, this violation. So the first correlation comes out to be 0.68, and the second one's 0.48, and the third one is minus 0.24. And so when we take the first plus the second minus the third, we get 1.4. 1.4. So it's what's strange is how the first were, have these moderately positive correlations, but the third one comes out negative. That's like difficult, impossible for three-way joint distribution to produce. Anyway, so 1.4 is greater than the boundary, 1, and it violates the Leggett guard, and there is no joint distribution. So again, we need to put these tables in separate contexts. They don't fit into a single joint distribution. They're contextualized by the pairs of questions. So how we're reasoning about intelligence or trustworthiness or dominance depends on what it's paired with. So what you're thinking about intelligence changes if you're thinking about trustworthiness versus you're thinking about dominance. So the pairs somehow affect these joint distributions. So this would be the last example. So this is an example from risky decision making. So this is just to show you that this kind of contextual reasoning is really very common and broad, ubiquitous. So this is with risky decisions. So this is a study by Tversky and Shafir, published in 1992. It's quite a while ago, but it's been replicated a couple of times. So, and it's a kind of gambling experiment. It's called a two-stage gambling experiment. But in this gambling experiment, participants are forced to play a gamble on the first stage. So they have to play the first stage, and they have an equal chance to win 100 or lose 50. Actually, they would win $1 or lose 50 cents in the actual experiment. Then they were asked to choose whether or not they want to play again. So they're forced to play the first time, but then they had a choice whether or not they wanted to play again. But Tversky and Shafir used 3 different conditions. In one condition, the players were told, well, suppose you won the first stage. Would you want to play again? So that's one of the conditions. And the second condition, suppose you lost the first stage. Would you want to play again? And then the third condition, you don't know the first stage. So the events are the outcome of the first stage and playing the second stage. Now, the question is, do all these events come from a common joint distribution? So Tversky and Shafir actually designed this experiment to test a rational principle decision-making called Savage sure thing principle. So according to Savage, this is the basis of subjective expected utility theory. This is one of the axioms. So Jimmy Savage wrote this book, Foundations of Science, maybe 1950s. And anyway, one of the axioms was, if you prefer to play, a gamble after knowing one state of the world, like a win, and you also prefer to play a gamble after the complementary state of the world, like you lost, then you should prefer to play the gamble regardless of what the first outcome is. And so it doesn't matter whether you know the first outcome, won or lost, you should still want to play. So that's the Savage sure thing principle. And this experiment was designed to test this by asking people if they won, would they play again? If they lost, would they play again? And would they play when they don't know? But what they found was something they called the disjunction effect. So when people were told they won the first game, 65% of them said they wanted to play again. So the majority choice was to go ahead and play the game again after winning. And if they lost the first game, still a majority, not as large, but still a majority chose to play the gamble again. So it seems like most people wanted to play it after a win. Most people wanted to play it after a loss. But when the first stage was unknown, all of a sudden now many people switched and didn't want to play it again. Only 35% chose to play it again in the unknown condition. So, and the majority pattern was to choose to win on play after a win, play after a loss, and not play after unknown. And so a lot of participants were violating the sure thing principle. And so this is another example where we need a contextual representation, because when the outcome is unknown, the probability that you want to play the gamble is only 0.35. But when you have the joint know the first outcome and then decide to play the gamble, in the joint situation of knowing the first outcome, well, the conditional probability that you want to play the gamble given a win is 0.65, and the conditional probability that you want to play the gamble again when you lost is 0.55. And according to the total probability, the probability that you play the gamble then should be some weighted average of 0.65 and 0.55, according to total probability, if all the events are coming from a common sample space. But we see that that average of averaging 0.65 and 0.55 has to be greater than 0.35. And so when they know the first outcomes, those probabilities we're getting don't match what we would expect when they don't know the first outcome. So whether or not they know the first outcome changes the distributions that we're working with. So again, the distributions be contextual depending upon whether outcomes are known or not known in the first stage. So yeah, an example where, basically the usual Bayesian hypothesis that all the events are coming from a joint probability space, and we have just calculated probabilities by marginalization. It's breaking down a lot in a lot of different decision-making tasks. And what we are trying to show is that quantum probability provides very good alternative probability theory for explaining this contextual nature of human reasoning. I mean, quantum probability was originally designed in physics, but events in physics also have this contextual nature. And so the contextual nature of electrons is kind of like the same that we're getting with human behavior. They share this kind of contextual nature. But what's the goal of quantum cognition? We're not trying to build a physiological or neurological theory of the brain, so that we're not proposing the brain as some kind of quantum computer. And there's a lot of interest in quantum consciousness, but we're not really working on theories of consciousness. What we're just doing is we're saying, look, quantum probability is an alternative probability theory. It's just as general, and maybe even more general than classical Bayesian probability. Excuse me. So we're just using this general probability theory, just happens to be based upon different axioms to predict judgment and decision-making behavior. So we're just using the theory mathematically to predict behavior because this behavior has this contextual nature. And so why quantum? Well, it's an axiomatic theory of probability, and human judgments are probabilistic, and these probabilities don't seem to obey the Kolmogorov axioms, and quantum theory provides a viable alternative. Now, there's a particular reason why quantum, I mean, there's lots of generalized probability theories out there, but why quantum theory? Well, quantum theory's got this non-commutative property, and that's something that's shared with humans. Humans have this non-commutative order, they're very order dependent. They're very sensitive to the order of the measurement. The measurements change the state of the person and produce these context effects. In fact, the principle of complementarity that was proposed by Niels Bohr for physics was actually a concept borrowed from William James. So, yeah, sorry, I'm losing my voice. Drink some water. Yeah, sorry. Yeah, so complementarity was actually an idea that came out of psychology and then got carried over into physics. Niels Bohr had a friend who was a psychologist, Rubin. Rubin had this Rubin's vase, this ambiguous figure. Rubin was a friend of William James and a friend of Niels Bohr. And Rubin told Niels Bohr about William James. But anyway, a last reason, an important reason, and this is really relevant to large language models, is that quantum probability is a probability theory that's placed in a vector space. So quantum theory is a method for assigning probabilities to events represented as subspaces of a vector space. So let's take a closer look at that idea. Oh, well, another advantage I should mention for quantum theories is that, why would the brain evolve a quantum reasoning system? Well, here's one reason we think. Suppose you have a game like a more general version of a prisoner's dilemma game, where you have n players, n different players, and each player has m choices. So in a prisoner's dilemma game, there's two players and two choices. So you got this 2 by 2 in a classic probability space. But if we had, like, let's say 8 players and each player had 3 choices, we'd have an 8 to the third power space. Well, a classical Bayesian probability theory requires building a joint probability space for all these m to the m combinations. So you have to have a joint probability for each player on each of the m values. And so the joint probability space grows at n to the m power, which is an exponentially increasing probability space. And Bayesians know about this problem. So Bayesian theory becomes unwieldy when you have too many variables and each with too many values. And so they have to impose a great deal of conditional probability assumptions, Markov type assumptions on the probability distribution, scale down the size of the probability space to a scale down number of parameters, because the space grows too large exponentially. So that's a problem with the Bayesian model. So maybe the brain or evolution designed the brain to get around this problem. Now, quantum probability works in a vector space. Now, the beauty of a vector space is that you have to, in order to interpret and assign numbers to events in a vector space, you have to choose a basis. So if you have an n-dimensional vector space, if you have an m-dimensional vector space, you have to use a basis. And what you could do to represent the n different players in this dimensional space is rotate the basis for evaluating the players. And so each player gets a new basis. So as you add players, you stay within a fixed m-dimensional space and only change the basis to represent different players. So the dimensional space doesn't grow as you add new players. It stays m-dimensional. So that kind of idea is an economy of representation of many different possible questions in a finite dimensional space. Now, the disadvantage of that, when you start representing different events by rotating the basis, is that you run into the uncertainty principle. So often you can't be certain about two different kind of events at the same time because you've changed the basis that you're using for evaluating those events. So that's one of the reasons we think nature might have designed the brain to be a quantum reasoner rather than a classical reasoner. Yeah. Now let's compare the probability theories, quantum, classical. So Kolmogorov axiom, of course, classical probability theory was developed by Laplace and Pascal even earlier, 1800s or 1700s, but it wasn't really axiomatized until 1933 by Kolmogorov. About the same time, von Neumann axiomatized quantum theory. So we have two different sets of axioms, one for classical probability theory and one's for quantum probability theory. And I'm going to briefly just try to go over them, but yeah. So the basic ideas are shown in this table here. So we'll take a look at the top of the table first. And so we have these principles labeled 1 through 4 here on this table. And in the middle column, we got classical assumptions and definitions for dealing with these principles. And on the far right, we have the quantum. So let's take a look at the idea of the space. Now, in classical probability theory, all the events come from a single sample space. So in the bottom down here in a picture of the red dots and blue dots, all the dots, red, blue, green, all those dots like are points in the sample space, like they're people we could sample. So those are the points in the sample space. So the sample space is a set, the universal set that contains all the points, all the things that could be observed can happen. Now, the corresponding idea in quantum theory is vector space. So let's say our sample space, to make it finite, to make things simple here, let's say our sample space was 100-dimensional. So we have a cardinality, I'm sorry, yeah, let's say we have a cardinality of 100 points in the sample space. So 100 points, probabilities there in the classical case. In the quantum case, we would replace the universal set with a universal vector space. So the vector space is called a Hilbert space. And so each point in the classical theory would go over to become a basis vector or an orthogonal dimension in the vector space. So if we had 100 points in the classical space, we would have 100-dimensional space in the vector space. Now, so we're replacing a universal set with a universal vector space, the Hilbert space. And now events, like an event, like in this bottom figure here, I've got, this is one of the classic examples of a conjunction fallacy that I didn't take time to mention, but the classic example is this feminist bank teller story. But this, well, maybe I'll say it now. I mean, Tversky and Kahneman use this story where you hear about a woman who graduated from UC Berkeley and she majored in philosophy and she was active in social movements. And now you're asked later on about this woman. What about this woman now, later on, after she graduated? And you're asked, well, what's the likelihood that she's a feminist? And that seemed likely to people. And then they're asked, well, what's the likelihood she's a bank teller? Well, that didn't seem very likely to people. But what was interesting was when they asked, what's the probability that Linda, this person from Berkeley, what's the probability that Linda's a feminist and a bank teller? They said that's more likely than bank teller. So feminist and a bank teller was judged more likely than bank teller. So that's an example of the conjunction fallacy. But anyway, on the left there, we have all the points represent the sample space. Green, red, and blue is the sample space in our classical model. And the event F is a subset. So the red dots is a subset of the sample space. That's the event. And the blue dots is a subset of the sample space, and that's the event. And the intersection, of course, the conjunction is the intersection, and that's the dots that's shared by the red and the blue circles. So in classical probability theory, events are a subset of a sample space. In quantum theory, though, we change the subset of a sample space to subspaces of a vector space. So on the right, what we have is this would really be a 4-dimensional space, but I don't put can't draw the 4th dimension in there. So only seeing 3 and 4. Now, we actually use much larger spaces than 4-dimensional. But this is a toy model. Anyway, suppose we have a 4-dimensional space as our vector space. That's our Hilbert space, 4-dimensional. And the event feminism is a subspace. It's a plane. You see that plane, that lightly shaded gray plane, that's our feminist subspace. And our bank teller is another subspace. So that's the dark shaded plane in that figure. And so events are subspaces of the vector space. Now, the reason why I think this is the critical place where things become quantum, because when you work with classical situation, when you work with events that are subsets of a sample space, you're working with a logic, a Boolean logic. So you have all these Boolean axioms, like you have, first of all, you have the axiom closure. So if feminism is an event, okay, and bank teller is an event, okay, well, then feminist and bank teller has to be an event too, because of closure, because it's the intersection. Also, you have commutativity. So feminism is an event and bank teller, feminist and Bank-Teller has to be the same as Bank-Teller and feminism because that's the intersection. And you also have distributivity. So the event Bank-Teller should be the event Bank-Teller and feminist and Bank-Teller and not feminist. And so you have all these axioms from Boolean axioms that are involved when you buy event as subsets. But when you change the subspace, you have a different logic. It's called quantum logic. It's a whole other field of logic. And quantum logic of subspaces is not Boolean. It's what we call partial Boolean, but it's not fully Boolean. So, for example, closure doesn't necessarily hold. So in this figure, for example, the event F, this plane representing F is one of the events in the subspace, one of the subspaces in the vector space. The event BT is another subspace in the vector space, but there is no subspace representing F and BT. Now, so when you evaluate feminist Bank-Teller, you have to do it in a certain order. So it's order dependent. So first of all, closure doesn't hold. There is no feminist and Bank-Teller event. There's a feminist and then Bank-Teller, or there's a Bank-Teller and then feminist, but there's no feminist and Bank-Teller. And so commutativity also breaks down. And finally, distributivity also breaks down. So all these axioms of classic probability theory can be violated in quantum theory. Now, in a way, quantum theory is a generalization of classic theory because if all the events in quantum theory commute, now these examples, this feminist event, this Bank-Teller event I have in this picture, they don't commute. But if the events commute, then they're going to behave classically. Now, so if all the events commute, then we're back in classical probability theory. So in a way, classic probability theory is a special case of quantum probability. It's a special case where all the events commute. So quantum theory is a generalization where some of the events commute and some of them don't commute. And so the non-commutativity is critical. Now, another thing about these theories is the way the probabilities are assigned to these events. So in classical theory, we construct what we call a probability function. So, P, that this probability function assigns probabilities between 0 and 1 to these events. So the feminist event, all the red dots gets assigned a probability. There's one green dot in there. Sorry. And all the blue dots get assigned a probability. So yeah, so we assign a probability to all the events using a probability function. Now, the way it works in quantum theory is a little bit different. The way what we start with is a state vector. So that psi, that arrow, that black arrow, is a state vector representing the state of the person. So when a person hears a story about Linda, she was went to Berkeley, she was a philosophy major, she was active in, social movements, they form a state vector. It's like a prior and a Bayesian model, but it's a vector in the Hilbert space. And Hilbert spaces can be complex valued, by the way, but we don't need to go into that right now. But so we have this vector sitting in the vector space that represents your prior knowledge, your knowledge from the story. And now, when you want to evaluate the probability that Linda's a feminist, you take that vector and you project that vector on the subspace for feminism. So that's that red arrow that goes from the black down to the lightly shaded. And that's the probability that the length of that vector, that projection, the length of that projection, which is kind of a brown shaded line at the bottom, that's the length of the vector for feminism. And I'm sorry, no, I'm sorry, back up. That's not right. So I have to come back to that later. Let me take this off of here so I can use my pointer. Can everybody see my pointer now?
Yes.
Okay, let me try this again. So here's our state vector, this black arrow. Now, if we were judging the probability of feminism, we would project this state vector on the subspace for feminism. I don't have a line here, but we'd have a line representing the the length of that projector, and we could get the squared length. So when we project onto a subspace and we take its squared length, that gives us the probability of that event. Like if we take the event psi here, that's this black arrow. I mean, we take the state vector psi here, that black arrow, and we project onto the dark shaded Bank-Teller subspace, then we get another projection. That's this kind of like lightly shaded line here. It's a shorter line right here. And so that's the probability of our Bank-Teller, the squared length of that vector. Now, if we want to get the probability that Linda's a feminist and then a Bank-Teller, we take our state right here and we first project on feminism and then we project on Bank-Teller and we get that projection. And you can see that the projection on the double projection from feminist and then to Bank-Teller is larger than the direct projection on Bank-Teller. And so that's how you get a conjunction fallacy with quantum theory, because this projection to feminist and then Bank-Teller, this line here is longer. It's got a greater squared probability than this direct projection right down here. And now if we went the other way around, we would get order effects. If we first project on Bank-Teller and then projected up on the feminism, we get a projection that was shorter than Bank-Teller. So feminist and then Bank-Teller gives you a big projection, but Bank-Teller and feminist gives you a short projection. So you get order effects, and you also get the conjunction fallacy. And so this figure shows you, basically how quantum theory can, with these non-commutative events, can produce non-commutativity and produce also violations of distributivity and the conjunction fallacy. Any questions on that figure? This is kind of important figure for the theory. I don't know.
So I guess if we're doing questions,
Yeah.
When people run this experiment, do they change the order in which they present Bank-Teller and feminist and then observe the results that you just demonstrated?
Well, yeah, we've done some that's a good question. And the answer is so far the results are not exactly coming out so clear. I mean, some people do this experiment looking at the order effect, and they don't find strong evidence for it. Let's put it that way. And other people did this experiment and looking for order effects, and they do find evidence for order effects. So there still needs to be more effect. That's a really important test of the model. And some of the experiments do find these order effects, but some of them found maybe some evidence against or less convincing evidence for. So yeah, it's still a bit of a controversy right there on that problem. Yeah, more research needs to be done on that. That's a really important problem. We're trying to do some experiments on that now.
All right, thank you.
Anything else?
I think we are good to continue.
Okay. All right. Yeah, so this is the basic difference between these theories. Yeah, so this is what I was just going over here. So in classic theory, your state is a probability function, but in quantum theory, your state, let me take this down here, is a unit length vector, S. And the way you compute a probability, I mean, the state is this unit length vector S. And the way you compute a probability in quantum theory is you take your state, which is this vector like that black arrow, and your subspace corresponds to a matrix, basically, a commutative matrix. I mean, not commutative, Hermitian, a Hermitian matrix, a projector, basically. So this is a vector here in a space. Like if we had a 100-dimensional space, this would be 100 by 1 vector. And this would be 100 by 100 matrix. And we multiply the two, that projects this state onto this subspace. Then we get the squared length, and that gives us the probability. And when we look at the probability of A and B in classic theory, of course, it's commutative. But in quantum theory, it's order dependent because we take our state, we first project on A and then project on B. we're not going to get the same result if we first project it on B then on A if these two matrices don't commute. So if they commute, we get the same result as classical. But if they don't commute, then we get a different result. So quantum theory, in a way, is a generalization of classic theory because we allow these matrices not to commute. And this is so in classic probability theory, the conditional probability is the probability of event B given A is the joint probability B and A divided by probability of A. In quantum theory, we might think of as a conditional probability of event B given A would be we first get the square projection on A and then B, and then we normalize it by the probability of A in a manner similar to the classic probability theory. So that's how quantum probability theory works. And yeah, so this slide maybe looks a little bit scary, but it's actually kind of simple. So let's take a look at this is the example where we had dyspnea and hemiparesis. And what we found was that the probability of dyspnea and hemiparesis was greater than the probability of hemiparesis by itself. Now, how could that happen? Well, I showed you in this example here how feminist and bank teller might be higher than bank teller. But let's just see it algebraically. So we don't depend on that simple toy model, but we have a general algebraic argument to explain these kind of things. So if we focus, here's the dyspnea and hemiparesis. Dyspnea and then hemiparesis. We first evaluate dyspnea and then hemiparesis. We're evaluating the more likely first and the less likely second. Here's hemiparesis, the probability of hemiparesis in quantum theory. We take our state, that's a story about this woman that's got this mental condition, and we project on hemiparesis. But we can sandwich in here the identity matrix, and then we can partition this identity matrix into dyspnea and not dyspnea projections that add up to the identity. And then we multiply through here. And this state right here in this line I'm showing you is the superposition state. So this is the famous superposition state in quantum theory. What it's saying in the superposition state is you haven't made up your mind about dyspnea. I mean, you weren't asked about dyspnea. So you're superposed between whether dyspnea is present or not. You haven't resolved that question yet. That's the superposition state. Now, when we take the squared length of the superposition state, we get this first term squared right here, and then we get the second term length squared right here, and then we get the cross product term. This term times this plus this term times that. That's the interference term. That's that's the famous interference term you have in quantum physics. That gives you like the double slit phenomena. So this interference this is what it is algebraically. But basically, this interference can be positive or negative. Now, in order to explain the conjunction fallacy, this interference has to be negative and sufficiently negative that it overcomes this positive contribution right here. So if this has to be positive, but if this is more negative than this is positive, then this whole sum that contributes to this H will turn out to be less than this term here, and that'll produce the conjunction fallacy. By the way, that same argument also, there's something called the disjunction fallacy. I didn't go over that because for lack of time. Yeah, I'm running out of time. Disjunction fallacy is where people will sometimes judge the event A or B to be less than the event A. And so, but the same exact model, same exact equation, same parameters, everything will produce both the conjunction and the disjunction at the same time. Anyway, this is the model applied to the categorization decision-making problem. It's the same model. Here's the model applied to the risky decision-making problem. It's the same model. This is the model applied to question order effects, and all we're doing is reversing the order of the projectors. So we see that quantum probability theory, the beauty of it is we've got these different phenomena that people have been studying for many years. They've always appeared like unrelated, and they have a different heuristic explanation for each one of these phenomena. But quantum theory uses the same axiomatic system, the same probabilities, the same explanation, and ties all these phenomena together in an elegant and simple manner, and helps us understand these things more coherently. Now, this question order effect is particularly interesting because we derived a theorem called the QQ equality for question order studies. And the QQ equality is a parameter-free, um, rotation-free, general a priori prediction. So this combination of like answers to questions, yes to A, then yes to B, plus no to A, then yes to B, minus yes to B, then no to A, plus no to B, times yes to A. Those combinations of probabilities that we observe in the data, that according to quantum theory has to be equal to zero. So the theory has to predict this. I mean, when we first derived this, we were scared because we thought we'd disprove our own theory. Yeah, so it's parameter free and a priori. It just comes from changing the order of these projectors. And what we find is that this predictor, this is a QQ plot. This is the predicted chi-square from our theory, and because there's noise in the data, and this is the observed. And the observed chi-square lines right up on the line of the predicted chi-square for the QQ equality. So this is across like about 80 different national surveys that looked at question order effects. So we've had strong a priori quantitative, prediction that's been satisfied. And that's a pretty strong test of the theory, stronger than any I've seen in social sciences. So in conclusion, quantum theory is a contextual probability theory for developing probabilistic models of judgment decision. And it provides a coherent account for puzzling violations of classic probability found in a variety of judgment decision-making studies, and it forms a new foundation for understanding widely different phenomena in decision-making using a common set of axiomatic principles. So if you're interested, you could get our book, Quantum Models of Cognition by Peter Bruza and myself. Okay, so I'll stop there and really thank you everyone for your attention.